The ocean beneath you is moving, right now. A river wider than any continent, carrying more water than every river on Earth combined, flowing through the Atlantic in a giant loop that has kept our world livable for thousands of years. We call it a current, but what it really is a heat engine. One that decides where rain falls, how cold your winters get, and how high the water rises on the shores of New York and Miami. And something is going wrong with it. Scientists have found the fingerprints of a slowdown stretching back decades. The water is changing, the loop is losing power, and the places most likely to feel it first, Europe, West Africa, the American coast, may not see it coming until it's already arrived. We're going to take you inside this hidden machine, into the science, the warnings, and the question no one can fully answer yet. How close are we to the edge? Picture a bathtub the size of an ocean. Now imagine it draining and filling at the same time, in a slow circle that never stops. That is the closest thing to what is happening beneath the surface of the Atlantic right now. The Atlantic is home to one of Earth's most powerful systems, a giant loop of water that stretches from the tropics all the way up to Greenland and back again. Warm water near the surface moves north, cold water at the bottom moves south, round and round for thousands of years without stopping. Scientists call it the Atlantic Meridional Overturning Circulation, but the name matters less than what it does. This loop moves heat, a staggering amount of it. Every second, the system pumps enough thermal energy northward to equal the output of more than 1 million power plants running all at once. Think about what that means on a human scale. The United Kingdom sits at roughly the same latitude as parts of Canada that are buried in snow for half the year. London and Calgary share almost the same position on the map, but London rarely sees a hard winter. Calgary is regularly buried under feet of snow. The difference, in large part, is this loop. The warm water flowing north releases heat into the air above it. That heat drifts east into Europe. It is the reason cities like Oslo and Edinburgh can exist the way they do, without the crushing winters their latitudes should demand. This is a system so large that it shapes where people can live, what crops grow, and how stable the weather is across an entire ocean basin. Generations have been born, grown old, and died without knowing it existed. And for most of human history it ran quietly in the background, completely unchanged. But the loop has a weakness, an understanding that weakness starts with something as simple as a pinch of salt. Cold water sinks. That is the engine at the heart of this whole system, and it works because of two things happening to the same water at the same time. Warm, salty water flows north from the tropics. As it moves toward Greenland, it loses heat to the cold air above. Cooling water gets heavier, and salt makes water heavier still, because salt adds density. So by the time this water reaches the far north, it has become something the ocean rarely produces. A mass of water so cold and so salty that it simply drops, straight down, mile after mile all the way to the seafloor. It sounds slow. It is slow compared to anything a person can see. But the sheer volume is impossible to picture. Every second, roughly 15 million cubic meters of water complete this plunge. That is about 6 times the combined flow of every river on Earth, happening quietly beneath the surface of the North Atlantic, every moment of every day. Once it sinks, it does not disappear. It begins a long journey south along the ocean floor, sliding beneath the rest of the Atlantic, eventually mixing into other oceans and slowly warming until, thousands of years later, it resurfaces somewhere far away and begins the whole journey again. This full loop, from the tropics to the deep north and back, takes roughly 1,000 years to complete. A single molecule of water entering the system today will not return to the surface until sometime in the 31st century. The loop is not fragile exactly. It has run through ice ages, warm periods, and every natural swing the climate has made for a very long time. But it has one vulnerability. The sinking depends on the water being heavy enough to drop. And right now, something is making that water lighter. The question scientists are racing to answer is how much lighter it can get before the sinking slows enough to matter. The answer has implications for everyone on Earth. In 1987, an oceanographer named Wallace Brucker drew a diagram on a piece of paper that would change how scientists think about the planet. The diagram looked simple, almost like something you'd doodle in class. A long loop with arrows, warm water going one way, cold water going another. He called it the Great Ocean Conveyor Belt. Before Bruker's diagram, most scientists thought of the oceans as relatively slow and stable systems. The atmosphere got the credit for dramatic climate swings. Bruker saw it differently. He had spent years studying the chemistry of old ocean sediments, and the patterns he found told him that the ocean had switched modes before, rapidly, and that those switches had driven some of the most extreme climate events in Earth's history. His conveyor belt idea was not just a picture, it was a warning. If the loop could be disrupted, he argued, the climate could flip in ways that had nothing to do with slow, gradual change. It could happen in decades, maybe less. People largely ignored him at first. The idea that an ocean current could reorder the climate of an entire hemisphere seemed too dramatic. Then the ice cores arrived. Scientists drilling into the Greenland ice sheet in the early 1990s pulled out a record of the past going back 100,000 years, layer by layer. What they found shook the field. The climate had not always changed gradually. It had lurched. Temperatures in Greenland had jumped as much as 18 degrees Fahrenheit in under a decade, multiple times. The pattern matched exactly what Bruker had predicted. One geoscientist who worked on those ice cores, Richard Alley, described drilling down through centuries of gradual change and then hitting a boundary so sharp that he said it felt like falling off a cliff. That cliff was the signature of the ocean system switching states. And what scientists are watching now in real time is the first evidence that the current may be approaching another edge. For most of human history, no one could actually measure this current. Scientists knew it existed. They could see its effects in ocean temperatures and climate patterns, but measuring it directly was like trying to weigh a river while standing on a bridge. You could see the water. You could not easily know how much. That changed in 2004, when a chain of instruments stretching across the Atlantic was switched on for the first time. The project stretched from the Bahamas to the Canary Islands. Hundreds of sensors, anchored at different depths, all measuring the same thing: how much water was flowing north and how much was returning south. Scientists called it a monitoring array. In practice, it was a speedometer built across an entire ocean. The first years of data were revealing in ways no one had fully anticipated. The current was far more variable than expected. It surged and slackened with the seasons. It had good years and bad ones. But underneath all that noise, a longer pattern was beginning to emerge. In 2010, the instruments picked up something dramatic. The current dropped sharply. Over a period of months, it weakened by almost a third. Sea levels north of New York City jumped by nearly 5 inches in just 2 years, as the ocean redistributed itself. That single event made clear just how directly this current affected the land around it. Since that dip, the system never fully recovered. Data from the array showed a slow but steady decline in average strength through the years that followed. Scientists were careful not to overinterpret a 20-year record in a system that operates on 1,000-year timescales. But the trend was hard to ignore. The monitoring array was the first continuous look at this system anyone had ever taken. And in its first 2 decades, it had already caught the current doing something that worried the people watching it most closely. The question was whether this was a temporary dip, or the beginning of something much longer. The fresh water is the problem, and it is coming from a place most people have never visited, flowing from something the size of a continent. Greenland holds the second largest mass of ice on Earth. If every piece of it melted at once, global sea levels would rise by more than 20 feet. For most of the last 1,000 years, the ice sheet gained in winter roughly what it lost in summer. It was roughly balanced. Then, in the late 20th century, that balance broke. The ice began losing more than it gained, year after year. Billions of tons of meltwater poured off Greenland and into the North Atlantic. This matters to the current because fresh water is lighter than salt water. When that melt hits the ocean, it sits near the surface, diluting the salty water beneath it. The current needs that water to be heavy enough to sink. Salt makes it heavy. Cold makes it heavy. But fresh water undoes both effects. It acts like a cap on the ocean surface, reducing the density of water that would otherwise plunge toward the seafloor near Greenland and drive the whole loop forward. Think of it like this. Imagine trying to keep a bonfire burning, but someone is slowly pouring buckets of water on the wood. They are not putting the fire out all at once, just keeping it a little damper each time. The fire still burns, but it burns lower and lower with every bucket. The Greenland ice sheet is those buckets, and the fire it is dousing is the engine of the current. Scientists have also measured an increase in rainfall over the North Atlantic, another side effect of a warmer climate. Rain is fresh water too, so the ocean near the sinking zone is getting hit from multiple directions at once, with melt from Greenland and with more rain from above, all of it working to make the water lighter, all of it working to slow the sinking. The current is still running, but the buckets keep coming, and each year brings more of them. South of Greenland, there is a patch of ocean that has puzzled scientists for more than a century. While nearly every other part of the Atlantic has warmed along with the rest of the planet, this patch has cooled. Sea surface temperatures there have actually dropped since the early 1900s, even as the world around it has grown steadily warmer. Scientists noticed it decades ago and called it the cold blob. At first, no one was sure what to make of it. Some thought it was just an unusual local feature. Others thought it was a hint of something bigger. For a long time, two explanations competed. Either the ocean in that region was losing more heat through its surface, pushed by changes in wind and clouds, or the current was simply delivering less warm water there because it was getting weaker. A series of studies in recent years, using satellite data, ocean buoys, and temperature records going back to 1955, have now pointed firmly toward the second answer. The blob is sitting where it is because less heat is arriving. The current is not delivering as much warmth to that corner of the ocean as it once did, and that drop in delivery is consistent with a current that has been slowing for decades. What makes the cold blob so striking to researchers is that it is sitting right where it should be, according to the models. If you run a computer simulation of what happens when this current weakens, the first thing that shows up is exactly this: a pocket of cool water just south of Greenland while the rest of the world warms. The models predicted the blob. The blob appeared. Scientists now treat it as a live fingerprint of the slowdown. The blob is not dramatic. You would not notice it if you were sailing through it. But it is one of the clearest signs in the entire ocean record that the system has already shifted from where it was 100 years ago, and the last two major studies on it landed with the same conclusion. The source of the cooling is not the atmosphere. It is the current. The current is already changing, and what comes next is what scientists cannot yet agree on. Before any satellite, before any monitoring array, scientists needed another way to look into the past. The ocean does not keep written records, but it does keep chemical ones, and for decades researchers have been reading them. The trick involves sediment pulled from the seafloor. Over thousands of years, tiny marine creatures live and die in the ocean, and their shells sink to the bottom, stacking up in layers the way pages stack in a book. The chemistry of those shells changes depending on what the water above them was doing. Temperature, salinity, the way the current was flowing, all of it leaves a faint trace in the calcium of those shells. Scientists can drill down into that sediment, pull up a core, and read the record one layer at a time, like flipping through pages backward through time. The deeper the layer, the older the water it represents. What those cores show is that the current has not always run the way it does today. It has weakened and strengthened many times. During some of the coldest periods in the last 60,000 years, it slowed dramatically. During warm periods, it ran strong. But the cores also reveal something more disturbing. The current that exists right now, in the 21st century, is the weakest it has been in at least 1,000 years, possibly much longer. A major study published using ice cores, ocean sediments, and coral records compared the current strength across more than 12 centuries of data. The conclusion was stark. The slowdown of the last 100 years stands out in that long record. It is not within the normal range of swings the system makes on its own. Something different is happening. The question that followed naturally was whether a current this old, this powerful, and this consequential could actually stop. Turns out, it already has, more than once. 12,000 years ago, the world was in the middle of warming up. The last great ice age was ending. Glaciers that had covered much of North America and northern Europe were retreating. Sea levels were rising. Things were, by all accounts, trending warmer. Then, in what geologists can now measure as the span of a few decades, the warming stopped. Temperatures in Greenland plunged by more than 20 degrees Fahrenheit. Europe went cold again. North America went cold again. The warming reversal lasted over 1,000 years. Scientists call this period the Younger Dryas. What caused it was exactly what scientists worry about today: a massive pulse of fresh water. As glaciers melted across what is now Canada, an enormous lake of meltwater had been building up behind a wall of ice. When that ice wall finally gave way, an unimaginable flood poured into the North Atlantic. Fresh water, vast in volume, lighter than the salty ocean below, it spread across the surface of the sea and shut down the sinking process near Greenland almost completely. The current collapsed, the heat engine stopped pumping, and within decades the climate of the entire northern hemisphere had lurched back toward Ice Age conditions. This is the template scientists are using to understand the present. The trigger back then was a sudden flood. The trigger today is slower, steadier, but functionally similar. Fresh water pouring in from Greenland year by year, doing the same thing to the same part of the same ocean. After the Younger Dryas ended, the current revived. It has been running relatively steadily ever since. That long stability is what made the last 2,000 years of human civilization possible, and it is exactly that stability that some researchers now believe is beginning to break down. The word tipping point gets used a lot in climate science, but for this current, it describes something very specific, something with a clear physical meaning that scientists have been studying for over 60 years. In 1961, a climate researcher named Henry Stommel built a mathematical model of how ocean circulation works. It was simple, just equations on paper. But it revealed something alarming. The circulation system had two possible stable states, one where it runs strong, like it does today, and one where it barely runs at all. The critical insight was that the system could flip from one state to the other, and once it flipped, it would not automatically flip back. The switch was one-directional. You could not simply undo what had been done. This property is called bistability. Think of a light switch, not the smooth kind on a dimmer, but the old-fashioned kind that clicks hard into position. You can push it gradually for a long time, and nothing happens. Then it clicks, and once it clicks, it stays clicked. Pushing it the other way does not reverse it automatically. You have to reach all the way over and flip it back. The ocean current works the same way. Freshening the water gradually year by year does not weaken the current smoothly. For a long time, the system compensates. Then it reaches a threshold. And past that threshold, it can shift rapidly and lock into a new, weaker state. The most troubling detail from Stommel's model, and from every more complex model built since, is that there is no obvious warning label on the threshold. The ocean does not announce when it's getting close. The current can look mostly normal right up until the moment it begins to change rapidly, which means by the time the shift is obvious, the point of no return may already be behind us. How do you take the temperature of something that is a mile deep, 2,000 miles wide, and moves in a loop that takes 1,000 years to complete? That is the problem scientists have been wrestling with ever since they decided they needed to actually watch this thing in real time. The monitoring array that went into the water in 2004 was the first serious answer to that question. But an array of sensors anchored to the seafloor between two specific points can only tell you so much. To understand the full picture, scientists use multiple approaches at once. Satellites measure sea surface temperatures from space. Floating robots called Argo floats drift through the ocean at different depths, measuring temperature and salinity as they go, then surfacing to send their data home. Research ships cross the Atlantic on dedicated sampling runs. Submarine cables originally built for communication have been repurposed to measure ocean properties near the seafloor. None of these tools, alone, gives a complete picture, but together they have built up a record of the current that grows more detailed every year. What that record shows, when you put everything together, is a current that has been losing strength since at least the mid-20th century. The rate of decline, measured in one study across the subtropical Atlantic, works out to roughly 1 unit of flow loss per decade. That is a unit that scientists use to measure ocean transport, where 1 unit equals 1 million cubic meters of water per second. The number sounds abstract, but losing one of those units per decade sustained over a century would leave the system in a meaningfully weaker state than the one that kept Europe mild for the last 1,000 years. The hard part is that scientists disagree about how much of this decline is natural variation and how much is a response to warming. The monitoring record is only 2 decades old. The current operates on much longer timescales. Separating the signal from the noise requires patience the instruments have not yet had time to provide. But the signal is persistent, and the noise keeps pointing the same direction. In September of 2025, the government of Iceland did something no government had ever done before. It placed the possible collapse of this current on the agenda of its National Security Council, classifying it as a national security threat. Iceland is a small island nation. Its entire economy depends on fishing, geothermal energy, and tourism. All three are deeply sensitive to the ocean temperature around it. For Icelanders, the current is not an abstract climate concern. It is the reason the island is livable at all. Without the warmth it carries north, Iceland's ports would freeze, its growing season would vanish, its fish would relocate to warmer water. Iceland's climate minister made the case directly, saying that this was a direct threat to national resilience, and that they could not afford to wait for long-term research before acting. This was the first time any specific climate event had been formally brought before the country's Security Council as a potential threat to survival. The move prompted attention far beyond Iceland. Scientists who had spent careers studying this current responded with a mix of relief and frustration. Relief, because a government was finally treating the science with the seriousness they felt it deserved. Frustration, because no larger nation, no country with a greater capacity to respond or to reduce the emissions driving the changes, had matched that urgency. Stefan Ramstorff, one of the most prominent researchers on this current, publicly praised Iceland's decision and said other countries should follow immediately. None of the major Atlantic nations, including the United States, had taken anything approaching a comparable step. What Iceland knew, and what more people are starting to understand, is that this current is not just a European problem. The effects of a serious slowdown extend across the entire planet. And the chapter most people are not yet thinking about involves a part of the world very far from the North Atlantic. Stand on the coast of West Africa during the summer. The rains have arrived, farmers have planted, rivers are filling. The whole season turns on those rains, and those rains turn, more than most people realize, on a band of rising air near the equator that follows the warmth. That band of rising, rain-producing air is called the tropical rain belt. It moves north and south with the seasons chasing heat. And the heat it chases is partly shaped by how much warmth the ocean current is pumping northward across the Atlantic. When the current runs strong, more heat reaches the northern hemisphere. The rain belt shifts north. West Africa gets rain. The Indian monsoon loads up with moisture. Parts of South Asia receive the water that hundreds of millions of people depend on to grow food. When the current weakens, the northern hemisphere loses heat relative to the south. The rain belt drifts south. Monsoons weaken. The rains that billions of people rely on shift or shrink. Researchers have modelled what a serious slowdown would do to these rain systems. The results are stark. Annual rainfall over West Africa could drop by roughly 30% across the monsoon season. The Indian summer monsoon would weaken. The East Asian summer monsoon would shrink. These are not small changes. These are the kind of changes that determine whether crops grow or fail, whether rivers fill or dry up, whether a village survives the year. More than 3 billion people live in areas sensitive to these monsoon systems. For them, the Atlantic current is not a remote scientific concern. It is part of the invisible infrastructure that keeps them alive, and none of them voted on how much ice Greenland sheds this decade. Open a map of the United States East Coast and trace your finger from Miami to Boston. Every city along that line sits on low ground near the water. Miami Beach, Charleston, New York, Boston. All of them already deal with flooding on bad storm days. All of them are watching sea levels rise, and all of them are going to feel the effects of a weakening current in a way that most Americans have not been told about. The current acts like a kind of invisible wall in the ocean. Warm water flowing north presses against the American coastline and creates a slight tilt in the water surface. The sea level on the American side of the Gulf Stream is actually a little lower than it would otherwise be, because the current is pushing water away. When the current weakens, that invisible wall relaxes. Water sloshes back. Sea levels on the East Coast rise faster than the global average. Scientists recorded exactly this effect during the brief slowdown in 2009 and 2010. Sea levels north of New York City jumped by around 5 inches in 2 years. That was from a short-term dip. A long-term weakening would add to the sea level rise already coming from melting ice and warming water, making the East Coast especially exposed. One analysis found that flood exposure in the New York area more than doubles under an extreme slowdown scenario. Cities that already spend billions managing storm surge and coastal flooding would face a future where the baseline has shifted permanently upward. Every storm that rolls in from the Atlantic would hit a coast that is already 5, 10, or 15 inches higher than it was a generation before. Miami, built almost entirely on flat limestone, has no natural elevation to retreat to. Boston's subway tunnels already flood in major storms. The future of the East Coast depends partly on decisions being made about carbon and ice thousands of miles away. And very few people in those cities know it yet. The Amazon rainforest is the largest tropical forest on Earth. It covers an area bigger than the continental United States. It produces its own rainfall through a system of evaporation and cloud formation so powerful that scientists call it a flying river. It holds more species of life per square mile than almost any place on the planet. It is also connected to the Atlantic current in ways that researchers are still working to fully understand. And a serious disruption of that current could flip the Amazon's wet season and dry season, swapping them entirely. The mechanism is the same tropical rain belt that controls monsoons over Africa and Asia. When the current weakens, the rain belt shifts south, delivering more rain to parts of the southern hemisphere that normally receive less. The Amazon's wet season comes at a different time than it does today. The dry season arrives when the rain used to fall. Trees adapted to one rhythm suddenly face the opposite. Models of this scenario found that the Amazon's precipitation patterns could change more dramatically from a current disruption than from climate change alone, and the Amazon is already under severe stress from deforestation and drought. A forest that has spent millions of years adapting to one seasonal rhythm cannot quickly adapt to the reverse. A destabilized Amazon matters far beyond South America. It is one of the largest stores of carbon on land. If enough of it dies back or burns, it releases enormous amounts of carbon into the atmosphere, which in turn drives more warming. Scientists call this a cascading effect, where one tipping element pushes another toward its own threshold, and that one pushes the next. The current, the Amazon, and the ice sheets may be connected in exactly this way, each one capable of pushing the others. The ocean is not just a heat engine, it is also a carbon sponge. Every year, the world's oceans absorb roughly a quarter of all the carbon dioxide that human activity releases into the atmosphere. Without that absorption, the planet would be warming much faster than it already is. The ocean is, in a very real sense, doing humanity a profound favour, and the current is one of the main reasons it can do that favour at all. Here is how it works. Carbon dioxide dissolves into surface water relatively easily. Warm surface water in the tropics absorbs some. But the real long-term storage happens in the north. When water near Greenland gets cold and sinks, it carries dissolved carbon with it, all the way to the seafloor, where it can stay locked away for centuries or longer. The sinking is the key. Without it, carbon that the ocean absorbs would just sit near the surface and slowly leak back into the air. The deep dive is what makes the storage permanent on any timescale humans care about. A weakening current changes this equation. Researchers have found a close relationship between how strong the current runs and how much carbon the North Atlantic can store. Weaker flow means less sinking. Less sinking means less carbon going deep. Less carbon going deep means more of it stays in the atmosphere, which means more warming, which in turn pushes more fresh water off Greenland and into the ocean, weakening the current further. This is a loop within a loop, and one study published in 2025 calculated that accounting for this carbon feedback alone would add significantly to the economic cost of a slowdown, costs that had not been included in any previous assessment. The ocean was doing quiet, invisible work, and we may be in the process of making it stop. One team of researchers decided they wanted an early warning system, something that could tell them the current was approaching its tipping threshold before it actually crossed it. The problem was that the current's behaviour looks mostly normal right up until it doesn't. The usual approach of watching for dramatic changes would arrive too late. What researchers needed was a signal that appeared before the shift, a kind of trembling in the system before the collapse. They found one. It involves fresh water transport near the southern edge of the Atlantic, close to the tip of South America. The current, as part of its loop, moves salt northward and carries fresh water southward. When the system is healthy, this exchange happens in a predictable way. But as the current weakens, the freshwater transport changes in a specific measurable direction. Researchers ran the available ocean data through their models and found that this signal had already moved. The measurement had crossed into the range that their simulations associated with the system heading toward its tipping point. This is an early warning, not a deadline. The current is still running. The warning says it is on a trajectory, and that the trajectory leads somewhere no one would choose. Other researchers looked at similar measures and found the same direction of change, with different estimates of how close the threshold actually is. The debate about timing is genuine. Some studies place the risk of a major shift decades away. Others suggest it could arrive within this century, or sooner under high-emission scenarios. The uncertainty is real. But the signal pointing toward a threshold is also real. And the question that follows naturally is what happens to the specific people, the specific places, on the day the science stops being uncertain. A major slowdown would reach Europe first and most dramatically, and when it arrived, it would come as a cold reversal on top of a warming world. Europe sits at high latitudes that should produce brutal winters, deep cold, and short growing seasons. The current has been compensating for that geography for thousands of years. London is warm enough to grow grapes because heat from the tropics flows north and releases into the air above the eastern Atlantic. Oslo and Stockholm enjoy conditions far more livable than their positions on the globe would suggest. A serious weakening would start to peel that warmth away. Researchers modelling a major slowdown found that winter temperatures in northwestern Europe could drop by 10 to 30 degrees Fahrenheit over the course of a century, not all at once, gradually but steadily, a cooling that runs directly against the warming trend everywhere else. Some parts of Scotland could begin to feel winters more like those of Norway. Parts of Norway could begin to feel winters like nothing that exists in Europe today. The growing season would shorten. Ports that stay ice-free year-round would begin to freeze. Agricultural land that currently produces wheat and barley would become unsuitable for those crops. One analysis found that a major collapse could reduce the land in the United Kingdom, suitable for arable farming, from roughly a third of the country to less than 1/10. That is a collapse in food production on an island of 70 million people. Heating costs would soar, energy demand would spike in winter, infrastructure designed for a mild European climate would face conditions it was never built to handle. And here is the part that makes it especially difficult to communicate. This cooling in Europe would happen at the same time that the rest of the planet is warming. The two things would run simultaneously, in opposite directions. A cold Europe and a hot world at the same time, a situation with no clean historical parallel and no obvious political vocabulary to describe it. That political gap is exactly where the next part of this story begins. The weather does not arrive with a label telling you which force shaped it. A cold snap in Britain feels like winter. A flood in the Netherlands feels like a storm. A drought in Spain feels like summer gone wrong. But behind all of it, changing the odds year by year, sits the current. The jet stream is a fast-moving river of air that circles the northern hemisphere at high altitude. It acts like a fence between cold polar air and warm tropical air, and it steers the storms that shape European weather. The jet stream draws its energy partly from the temperature difference between the cold north and the warm south. When the current delivers less heat to the North Atlantic, that temperature contrast weakens, and a weaker contrast means a wobblier, slower jet stream. A wobbly jet stream does not just bring different weather, it brings stuck weather. When the stream meanders and slows, weather systems lock into place for days or weeks at a time instead of moving through. Rain events become prolonged floods, dry periods stretch into droughts, cold spells linger for weeks instead of days. The extremes are not necessarily bigger in absolute terms, but they persist far longer than before. Researchers have already linked changes in the North Atlantic, including the cold region that sits just south of Greenland, to summer heat waves and blocking patterns over Europe. The mechanism is subtle, but the signal has been growing. Seasons that used to be turbulent and varied are becoming seasons dominated by one weather pattern that parks itself and refuses to leave. This is one of the ways the current reaches into daily life without announcing itself. No headline says, The heat wave that just killed crops in southern France was extended by a weakening ocean current. The connection exists, but it is diffuse, statistical, and hard to communicate. And that difficulty in communication is part of what makes the whole situation so hard to address. The North Atlantic is one of the most productive fishing grounds on Earth. Its cold, nutrient-rich water supports enormous populations of fish, including many species that have fed coastal communities on both sides of the ocean for centuries. The current is what puts those nutrients in the water. As the system runs its loop, it pulls cold, deep water toward the surface in certain regions, and that deep water carries the dissolved minerals that phytoplankton need to grow. Phytoplankton are tiny, barely visible organisms, but they are the foundation of the entire ocean food web. Every fish, every whale, every seabird that feeds in the North Atlantic ultimately depends on those tiny organisms blooming in sufficient numbers each spring. A slowdown in the current disrupts the upwelling that brings nutrients toward the surface. With less nutrient-rich water rising, phytoplankton blooms shrink. Smaller blooms support fewer small fish. Fewer small fish support fewer large fish. The entire pyramid shrinks from the bottom up. One major study published in 2025 modelled what a serious weakening would do to marine life across the entire North Atlantic. It found a sharp decline in total ocean biomass, concentrated in the subpolar regions near Iceland and Greenland, where the current's effects are strongest. Commercial fish species, the ones that fill boats and fill plates and pay for fishing communities around the North Atlantic coast, would either decline or relocate to different, harder-to-reach waters. Iceland knows this. Its economy and its identity are deeply tied to the ocean around it. And in November of 2025, Iceland's government became the first in the world to formally name a possible shutdown as a national security threat. The fishing grounds, the ports, the food, the livelihood of a nation sitting at the top of the Atlantic. All of it depends on a current that has been running, quietly and reliably, for thousands of years, and all of it is at risk in ways that the countries further south have barely begun to account for. In April of 2026, a team of researchers at a French university combined decades of ocean data with climate models in a new way. They applied a statistical technique that let them use real measurements to correct for weaknesses in the models, and the answer they got was worse than the models alone had predicted. Previous estimates suggested the current would weaken by around 30% by the end of the century. The new analysis, corrected against actual observation, put the figure at 50%, a 50% weakening by the year 2100 under a middle-of-the-road emission scenario. Stefan Rahmstorff, one of the leading scientists on this question, summarized the finding directly. The pessimistic models, the ones that showed the steepest decline, turned out to be the accurate ones. The most alarming projections were right. 50% is not a total shutdown. The current would still exist. But it would be doing half the work it does today. Half the heat moved northward. Half the deep water formation near Greenland. Half the transport of nutrients. Half the carbon going down into the deep ocean. Half the influence on every weather system it currently shapes. Think of a car engine running on half its cylinders. The car still moves, but it cannot handle hills. It overheats easily. It stalls under pressure. A current running at half strength can still function, but it loses much of its resilience, and a system that has already lost half its strength is far closer to the threshold, where losing a little more becomes losing everything. The researchers who published this study did not say collapse was certain. They said the models showing strong weakening were the realistic ones, and a world where the most alarming projection is also the most accurate is a world where the gap between where we are and where we do not want to be is narrower than most people have been told. Researchers at the Potsdam Institute for Climate Impact Research published a study in April of 2026 that added a new dimension to everything already known about the current. The question they asked was simple. If the current were to collapse, what would happen to the carbon the ocean was storing? The answer was serious. A collapse would flip the Southern Ocean, one of the most important carbon sinks on the planet, from a region that absorbs carbon dioxide to one that releases it. Over hundreds of years, that reversal would push an additional large volume of carbon dioxide into the atmosphere, equivalent to a substantial fraction of what human civilization has emitted in the modern era. And that extra carbon would add roughly 0.2 of a degree Celsius of additional warming, on top of everything else already happening. This is a feedback loop in the truest sense. The current weakens because the climate warms. If the current collapses, the climate warms more because the ocean releases carbon it was storing, which puts more pressure on everything else that is already under strain. But the same study revealed a detail that changes the nature of the problem entirely. At pre-industrial levels of carbon dioxide in the atmosphere, around 280 parts per million, the current could collapse and then recover. Push the fresh water forcing away, and the loop would restart. The damage was reversible. At 350 parts per million or higher, the behavior changed. The current could still collapse, but once it collapsed, it would stay collapsed. The atmosphere at those concentrations fundamentally altered the current's stability. Flip the switch, and it stayed switched. Recovery became impossible on any timescale relevant to human civilization. The atmosphere today sits at around 430 parts per million. It has been above 350 for decades, and it is still rising. Which means the window in which a collapse was reversible has already closed. The current is still running, but the situation it exists inside has permanently changed. Some researchers decided that understanding the risk was no longer enough. They wanted to know if there was anything that could actually be done. One answer arrived in April of 2026 from two researchers at Utrecht University. Their idea was startling in its simplicity and its scale. Build a dam, a massive dam stretching 50 miles across the water between Alaska and Russia. Seal off the Bering Strait entirely. The logic starts 3 million years ago, during a period called the Mid-Pliocene. Back then, the land bridge between Asia and North America still existed, closing off the Bering Strait naturally. During that period, the current ran stronger than it does today. The researchers reasoned that if sealing the strait coincided with a stronger current in the past, maybe sealing it again could help stabilize the current now. Their models showed that under certain scenarios, closing the strait could alter the flow of fresh water between the Pacific and the Arctic, helping maintain the salinity balance the current needs to function. In some runs, it delayed or prevented collapse. The scientific response was cautious. The researchers themselves called it a proof of concept, not a ready plan. Other scientists noted that the effects were uncertain, that the ecological consequences for the Bering Sea, one of the most productive marine regions on Earth, were not analysed, and that a dam might make things worse in some scenarios. Stefan Rahmstorff, whose career has been spent studying exactly this problem, said he was not a fan of the idea. What the proposal revealed, more than anything, was the state of the conversation. Scientists were now seriously discussing feats of engineering that would rank among the largest construction projects in human history, not because they wanted to, but because the alternative futures looked bad enough to warrant thinking about absolutely everything. The most important finding of 2026 arrived quietly in late spring as a scientific preprint. It had not yet been peer-reviewed when it circulated, but the team behind it had run an extraordinary volume of computer time to answer a single question. Was it already too late? The researchers modelled the current under 21 different emissions pathways, running each one across 62 variations of their climate model, tuned to match real ocean measurements. The combined computation burned through more than 400,000 model years of simulated time, all to answer one question about our own. Their answer was probabilistic, and it was not reassuring. Even under the most optimistic scenario they tested, where global emissions peaked immediately and Greenland meltwater was held at conservative estimates, they found at least a 10% chance that collapse was already committed, already locked in, happening eventually, regardless of what the world chose to do from this moment forward. In a worse scenario for Greenland ice melt, that probability rose to 23%. Under continued high emissions, it climbed to 80% by the end of the century. 10% may sound small, but 10% is the kind of number that warrants serious preparation. A 1 in 10 chance that a bridge will collapse is not a bridge you drive a school bus across. A 1 in 10 chance that a plane will not land is not a flight you get on. The researchers were careful to note that these estimates carry uncertainty, that a single model is not a verdict, and that the exact numbers could shift with more sophisticated tools. But their framing was deliberate. They were not asking when the collapse would happen. They were asking whether we had already guaranteed it, and the answer, in at least some fraction of the possible futures, was yes. We had already made a decision by not making a decision, and the ocean had been keeping score. The science of this current is full of genuine disagreement, and that disagreement is worth taking seriously, because it is not like the kind of debate you see in politics. It is scientists with different tools, different data, and different methods arriving at different estimates of the same underlying truth. The truth exists. The uncertainty is about how close we are to it. On one side of the debate sit researchers who have found strong early warning signals in ocean temperature records, sediment cores, and monitoring data. They read those signals as evidence that the current is losing stability rapidly, and that a tipping point may arrive within decades. Their models show the most alarming trajectories as the realistic ones, and their papers have been published in top scientific journals and taken seriously by governments, including Iceland's. On the other side sit researchers who point out that the monitoring record is short, barely 20 years of direct measurement for a system that operates on 1,000-year timescales. They note that the early warning signals are uncertain, that some high-resolution models show more stability than the lower-resolution ones used in most projections, and that the official assessment from the world's largest body of climate scientists still holds that an abrupt full collapse before the end of this century is unlikely. Both camps agree on the central fact. The current is weaker today than it was 1,000 years ago, and it is weaker now than it was 50 years ago. Both camps agree that continued warming will weaken it further. The disagreement is about pace and threshold, not about direction. This distinction matters enormously for how we think about the risk. A driver who knows there is a cliff somewhere ahead and knows the car is moving toward it has good reason to slow down. The uncertainty is not about whether the cliff exists, it is about exactly how far away it is. And the people who have studied the road most carefully are telling us the distance is shorter than the maps used to say. Tipping points are usually described as a single event, a moment when one system crosses one threshold. But the current does not exist in isolation. It is one piece of a larger puzzle, and the pieces are connected to each other in ways that make the whole far more fragile than any one part. The Greenland ice sheet is melting and sending fresh water into the North Atlantic, weakening the current. That is already happening. What is less discussed is the feedback loop that runs in the other direction. A weakened current changes ocean temperatures around Greenland's coast, causing more melting, sending more fresh water into the ocean, weakening the current further. One system drives the other, which drives the first one again, in a loop that can accelerate beyond what either system would do on its own. The current is also connected to the Amazon rainforest through the tropical rain belt. A collapse of the current would shift that belt, disrupting the Amazon's rainfall. But the Amazon is already under pressure from deforestation. If it loses its rainfall on top of that stress, it could begin to transform from forest to a drier, more open landscape, releasing the enormous amounts of carbon it currently stores. That carbon enters the atmosphere. The atmosphere warms more, which puts more pressure on the Greenland ice sheet, which sends more meltwater into the North Atlantic. One study estimated that there is roughly a 1 in 4 chance that, without major emissions reductions, at least one of the world's major tipping systems, the current, the Amazon, or the polar ice sheets, will cross its threshold before the end of this century. They are not independent dice rolls. The odds of one tip increase when another tip occurs nearby. Scientists call this a domino effect, and they have spent recent years building the case that the dominoes are already leaning toward each other. The hard truth is that the single most powerful lever for protecting the current is also the most basic and the least glamorous: burning less fossil fuel. Every fraction of a degree of warming adds pressure to the system. Every fraction of a degree avoided reduces that pressure. There is no more complicated version of this. Researchers at the University of Reading published a major analysis in June of 2026 that put it plainly. Every fraction of warming changes the odds. Every ton of carbon left unburned is a small push away from the threshold. The math does not favour passivity, and it does not punish early action. Some of that reduction has to happen at the level of governments, energy systems, and industry, changes that individuals cannot make on their own. But emissions are not just a policy abstraction. They are the sum of billions of individual decisions made every day about how to travel, what to eat, how to heat homes, and what to buy. The richest 10% of people on Earth produce roughly half of all lifestyle-related emissions. Every meaningful shift in how those people live has a disproportionate effect on the total. Stefan Rahmstorff, who has spent more of his career studying this current than almost anyone alive, put the priority as directly as possible. The most important thing the world can do is cut emissions as fast as possible. The world's average temperature in 2026 is likely to pass the 1.5-degree target set in the Paris Agreement. The time is short, but the physics of the situation rewards faster action and punishes delay in a way that is unusually direct and unusually clear. Every decade that passes at high emissions moves the current closer to a threshold that may be permanent. Every decade of serious reductions buys distance from that threshold. The ocean cannot vote, the ice sheet cannot lobby, the phytoplankton that feed the food chain cannot organize. All of those systems depend, in ways that took centuries of science to understand, on decisions made in the next 20 years by the people alive right now. In the 1990s, a geoscientist named Richard Alley was drilling into the Greenland ice sheet, pulling up cylinders of ice that contained a record of Earth's climate going back hundreds of thousands of years. Layer by layer, the ice told the story of slow change, small shifts, gradual trends. Then the team hit a layer that marked the end of the Younger Dryas, the 1,200-year cold snap that the current's earlier shutdown had created. Alley later described the experience of reading that layer in the ice. One moment, the record showed cold. A few layers further, it showed warm. The boundary between them was razor thin. He said it felt like falling off a cliff. That boundary in the ice was not just a moment in Earth's history. It was a warning encoded in frozen water, waiting 12,000 years to be read. The shift had happened fast. The climate, which appeared stable up until that moment, had simply jumped from one state to another. The current today is weaker than it was when that boundary was laid down. The fresh water forcing it faces today comes from a warmer Greenland, a more active Arctic, and a global water cycle that has intensified with rising temperatures. The pressure building on the system is of a different character than the melt from a single ice lake 12,000 years ago. It is slower, more distributed, and continuously increasing as long as the planet continues to warm. What Alley found in that ice core was not just a piece of climate history, it was a demonstration of what the current is capable of. Stability for a long time, and then a rapid shift that rewrites the climate of an entire hemisphere in decades. The cliff is real, and the question is how close we are to the edge. There is a way to hold this story that does not feel overwhelming, and it starts with understanding what the uncertainty actually means. Uncertainty about when a tipping point will be reached is not the same as uncertainty about whether one exists. Uncertainty about the exact size of the risk is not the same as uncertainty about whether the risk is real. The current is slowing, the fresh water forcing is increasing. The models that predicted this are being confirmed by real measurements. The fingerprints in the ocean match what the models said they would look like. All of that is solid ground. What is uncertain is timing. The current could hold closer to its present state for decades. It could weaken significantly within 20 years. Some models say one, some say another. But the range of possibilities has a common thread running through all of them. The outcome is not fixed. It depends on choices still to be made, and choices that reduce emissions pull every version of the future away from the worst outcomes. Researchers who have spent their careers studying this problem are not paralyzed by the uncertainty. They're energized by the stakes. They're publishing, warning, modeling, and speaking to governments with a frequency and urgency that has grown year by year. They're building better instruments, deploying more monitoring equipment, refining models to capture processes that were previously invisible. The science of this current has advanced more in the last 10 years than in the previous 50, and what it has revealed is a system of extraordinary importance that is changing in real time in ways that should demand the same level of attention we give to things that are visibly on fire. The ocean does not smoke, it does not make noise, it changes slowly in ways that are hard to see from shore. But the instruments are watching, the data is coming in, and the picture is getting clearer every year. What it shows is a world that built its civilization on a foundation it never fully understood, and is now watching that foundation shift for the first time in human memory. Every number we have talked about carries uncertainty. Every projection carries error bars. The current is not guaranteed to collapse. The models do not agree on exactly when or how much it will weaken. Scientists are still debating how to read the early warning signals, and some researchers warn that alarm-heavy media coverage makes the problem harder to address, not easier, because it can produce a sense of fatalism that discourages action. Those are real concerns. The science is not a verdict. It is a set of probabilities, a set of trends, and a set of consequences that follow from those trends. The probabilities are worrying. The trends are moving in one direction, and the consequences of the worst scenarios are large enough that even a moderate probability demands serious attention. Think about the way insurance works. You buy car insurance even if you are a careful driver, because the consequence of an accident without it is severe enough that the small probability still justifies the cost of preparation. The current represents something similar, except the insurance in this case is action on emissions, and the premium is paid every year in the form of choices made by governments, industries, and individuals. The researchers who study this system most closely are not resigned to the worst outcome. Many of them make the case carefully and with evidence that rapid emissions reduction changes the math in meaningful ways, that the range of outcomes narrows in a better direction with every fraction of a degree avoided, that the threshold, wherever it sits exactly, is easier to stay behind if the world approaches it more slowly. The ocean has been running this current for thousands of years, in every ice age, every warm period, every chaotic swing the planet has made. It has always found a way. The question we are now asking it to answer is whether it can keep running while we pour more fresh water into it every year, faster than at any point in the last 12,000 years, and whether we will slow that pour before we find out the answer the hard way. The story of the Atlantic current is still being written. The scientists watching it are paying attention. The data is still coming in, and the next decade will tell us more about what kind of story this turns out to be than all the centuries before it combined. Take a step back from the numbers and the models and the warnings, and hold the full picture for a moment. Human civilization grew up inside a climate that was unusually stable. The last 12,000 years, roughly the entire span of written history, agriculture, cities, and everything we recognize as the modern world, all of it unfolded during a period when the current was running strong and steady. The monsoons were reliable, the winters in Europe were manageable, the coasts of North America did not regularly flood, the Atlantic fisheries fed millions. None of that was guaranteed. The current had collapsed before, multiple times, in circumstances that look in some ways like a less extreme version of what is happening today. But in the geological lottery that determined which era humans would build civilization in, we drew a winning ticket. The current was stable, the heat was distributed, the rain fell in the right places. The civilization we built on top of that stable foundation is enormous. 8 billion people, global supply chains, cities on every low coast, agriculture tuned to specific temperature ranges and rainfall patterns, a world of precision, of expectation, of systems that function within narrow tolerances. The current is not collapsing today. The ticket has not been revoked. But the conditions that stabilized the climate for the past 12,000 years are now changing at a pace the system has not experienced in that entire span. We are not wandering bands of hunters who can follow the food. We are a civilization of 8 billion people with fixed cities and fixed farms, and a fixed expectation of where the rain will fall. And the force that kept the rain falling in the right places, for every generation of every person who ever lived in recorded history, is now carrying a load it was not built for. The scientists who study this current have a particular relationship with their work. Many of them have spent entire careers on a question that most people have never heard of. They publish papers that few outside their field read. They give talks at conferences. They brief governments. They watch the data come in, year after year, and they update their estimates. What drives them is not fear. It is the awareness that the system they are watching is consequential beyond almost anything else in the physical world. Ocean circulation is not a niche topic. It is the hidden infrastructure beneath the climate of the entire planet. Many of these researchers have watched the conversation around their work become politicized and simplified in ways that frustrate them. They see headlines that say collapse is imminent. They see headlines that say the current is fine. The truth, as they see it in the data, sits in between those extremes but tilts consistently toward concern. They continue to publish. They continue to refine the models. They are building the next generation of monitoring instruments, a more extensive network of sensors that will give them sharper data over the next decade. They are hoping the political will to act catches up to the physical reality before the gap between them becomes uncrossable. And they are watching, with an attention that is both professional and personal, a thing that most people will never see. the deep ocean moving, the cold water sinking, the loop turning, the heat flowing north, the foundation holding, for now. The final thing to understand about this current is that it is not waiting for us to understand it. It does not pause while the models improve. It does not halt while the political debate resolves. It runs, as it has always run, driven by the physics of salt and temperature and density in an ocean that is older than the human species. But it is also changing as we watch. The measurements are real. The trend is real. The fresh water pouring off Greenland is real. The warm water where cold water used to form is real. The cold blob sitting south of Greenland is real. The sea level rising faster on the east coast than the global average is real. These are not models. These are observations. Physical changes in the physical world happening now, measured by instruments in the actual ocean. The current has been doing its job for the entirety of human civilization, and for far longer than that. It has moved heat, stirred nutrients, stored carbon, shaped monsoons, and held the climate in a range that made it possible for our species to do everything we have done. That is not a small debt. What happens to it in the next 50 years depends on choices that are not yet made. The science has done its part. It has mapped the system, identified the risks, quantified the uncertainty, and delivered the warning with as much clarity as a system this complex allows. The answer to the question of what comes next is not written in the ocean. It is being written right now, in decisions made by people who, for the most part, have no idea how much is riding on them. This is not a story about the end of the world. It is a story about a machine, a real physical machine made of water and salt and temperature and gravity that has been running for longer than humanity has existed. A machine so large and so quiet that almost no one knew it existed until very recently. And a machine that, for the first time in its long history, is being tested by something it did not evolve to handle. The scientists who watch it are not giving up. The instruments are running. The data is coming in. New studies are being published every month. Some of them bring alarming news. Some bring nuance. Taken together, they tell the story of a community of researchers that understands, better than anyone else on Earth, how serious the situation is and how much remains undetermined. What they know for certain is that the current still flows, that the sinking still happens, that the loop still turns, and that every year of serious action on emissions is a year the current has more room to hold. Every fraction of warming avoided is a fraction of fresh water that does not pour off Greenland. Every ton of carbon that stays out of the atmosphere is a small push away from a threshold that no generation after us will be able to push back from if we cross it. The ocean beneath you is moving, right now. A quiet loop of water that has been keeping the world the way it is for longer than we have been keeping records. It is still running. The question that falls to this generation, in a way that has never fallen to any generation before, is how long we keep it that way.